As we grow, our populations soar and our cities are pushed to their limits. Their webs of transportation networks encasing continents. We further our opposition to nature, intensifying environmental threats and social uproar call into question the motives and limits of our cities, requiring a radical redefining of the city condition. The city is not defined by clusters of people or structures, but rather as a set of connected, intertwined, and competing systems. These systems have become normalised to the point of blind acceptance on Earth's cities as a form of collective expectation. Yet, do they exist in their optimum state for a post-industrial revolution world? Why are systems of capital central to our cities? Why do orthogonal grids propagate areas of density? These questions need to be interrogated as a response to the rapidly increasing and densifying populations of Earth, with acknowledgement of climate issues. Our own preconceived notions and understanding of the city condition limit our creativities in its development. As such, to speculate on a condition for Earth, we have first considered the generation of a new city on Mars. This presents two opportunities for Earth. Firstly, by moving infrastructure such as mining and manufacturing to Mars, the essential systems for Earth can be redefined. Offloading these systems onto Mars allows the terrestrial city to grow and lose density. The other outcome is a rethinking of the previously thought uninhabitable, Earth being far vaster than the reach of human development. As a testing ground, we have split a Martian city into its four essential systems for survival: settlement, energy, food, and mining. Each of these systems were tested on towards an optimum state. This optimum state was defined as one that is feasibly possible, promoted survival, and had an aspect of the hyperreal, that is, an alien rediscovery of the familiar. These settlement systems investigate the use of artificial intelligence in space exploration, searching for features of interest, for example, working with mining systems to select appropriate rock and soil targets for analysis. There is also an opportunity to track changing landscapes on Mars to benefit the development of other systems. Some of the iterations illustrate the interaction between mining and settlements to investigate the landscape conditions. A few others give an idea of the initial stages of occupation. The cumulative process of the AI settlements gradually evolves from that of few to many, sparse to dense settlements. The third set is AI identifying a previously undiscovered cluster of small craters. The AI settlements are broken down into various subsystems. Mission design and planning to obtain technical data and provide info for specific queries. Navigation systems to study and explore the potential for the development of mining, energy, and food systems. Space debris identification, identifying space debris that poses serious threats to existing space infrastructure. And monitoring systems. For example, visualization of solar radiation estimation for informed decision making. There can be no life without energy. Our modern survival and level of comfort is intrinsically linked with our access to electricity. Not only does this electricity serve to power our other systems, such as construction, mining, smart farming and more, It harnesses the power to further technological improvement through AI, computing, and research. While considerations were given to systems such as geothermal energy, the most scalable and easily established source of power is solar photovoltaic cells. With these panels, the AI quickly established rules for distributing the solar panels on areas of raised landscapes, enabling better access to the sun. The resultant scattering created new compositions for solar panels, extending their purpose beyond pure electrical generation into a new natural garden-like condition. Inspired by methods in Ridley Scott's The Martian, agriculture and specific farming of food was dependent on the systems of settlement in housing the climate required to do so. With the speculation that the soil on Mars would be suitable to grow crops of a certain specification and the assistance of the AI tool, we were interested in synthesizing how these farms may be translated and transported, if possible, to the Martian terrain. High contrasting farm images resulted in more resolved images. A clear distinction between the farm and landscape allowed the AI to generate more reasonable outcomes. It could be speculated that due to wind speeds of Mars, these food systems would be nestled within excavation on newly implemented mining systems on lower terrains. Attempting to situate the farm in these environments without simply texture mapping the landscapes gave a clear indication of percentile in which these systems could be developed. The existing and widely exploited resources on Earth are in the stage of increasing consumption. As non-renewable resources, mineral resources will face the reality of exhaustion sooner or later. This forms a study into the application of AI in mining under the conditions of a Martian landform for the construction of a Martian colony. While investigating different mining modes, including potash evolution ponds, salt flatten evolution ponds, the iterative pictures show a variety of possibilities of Martian mining in the control experiment. These iterations explored a future system of possibilities within a changing terrain of Mars. Siting the project on a single crater on Mars allowed for the generation of a series of speculative futures, each with its own narrative. From the hopeful blossoming of planted farming life to the grim skeleton landscape of mining gone unregulated, here we pondered on how a future on Mars might develop. To shelter agriculture from extreme turbulent winds experienced on Mars, mining is essential in excavating a terrain required for farming. With Mars's ice layers below the surface, food may also become dependent on mining's capabilities to reveal this frozen water, unlocking the ability to farm hydroponics such as kelp due to its fast-paced growth. Combining multiple systems allowed for studies into the interaction of these systems from isolation into a connected city infrastructure. Here, the AI was given curatorial control over the prioritization of systems for the survival of the colony. Emerging from this were a series of decentralized cities, defined not by their grids and systems of capital, but by necessity of survival. As such, logic such as solar panels being near settlement to reduce electricity loss in transportation and mining located far away became the dominant language of the speculative cities. As part of our research into redefining what is considered habitable on Earth, we considered an example site of the largely uninhabited Namib Desert in Namibia. Here, Using the same processes as Mars, a series of speculative cities were formed. These cities placed emphasis on nature, renewable energy production, and medium-density housing arrangements. By speculating into potential futures, such as flooding caused by melting ice caps, the city was able to morph and breathe based on the available landscape. Our approach also sought to tackle the contradictory nature between the city and the natural. Isolated from access to terraforming and bioredevelopment, a city or settlement on Mars must be accurately and carefully planned in accordance with the landscape to ensure survival. It is the response to the natural that allows the city on Mars and the one back on Earth to be read differently. Life on Mars is likely to take the form of shelters made from existing surface conditions, located near subterranean water, heat, and resources. On Earth, however, resource abundance sees these restraints freed, the surface instead heightened into a garden-like condition among systems of housing, smart farming, smart mining, and energy production.